some bypassing, and some going to, what are these? And specifically, what's the difference between these ones and these ones? Excellent. Low pressure compressor, high pressure compressor. It's hard to say. And you can see it's nicely labeled. Our high pressure compressor goes to our high pressure turbine, low pressure compressor, and if it's a just dual, not triple spool, the fan is on the same spool as the low pressure compressor going through in between to the low pressure turbine. And what is happening in these compressors? I want components and I want what's happening up there.
So the rotor accelerates the air and the stator blades increase the pressure.
Perfect. And what constitutes a stage of the compressor? Rotor stator. Very good. So we come right to, it's a little harder on this diagram to see what's happening in here, but at the end of the compressor, what is that component? Diffuser. And what does it do to the air? Increasing pressure. Yes, it's not getting compressed anymore because that's ended over here, but it is increasing pressure. And what is this section here? And what is that doing to our air? Expanding it, heating it. And what two components did we mention are unique to our combustor section? Fuel nozzles and igniters. Curious little side note. So on the Kodiak, last night when they were taking the passengers for a ride, they went to turn the engine on one of the rides, and the igniters were not igniting. So they had to replace the igniter box this morning.
They just did a run-up.
And it worked. Well, he said it's very rare for those to go out. So Michigan Air, I don't know. Don't like it. What are three types or styles of combustors? Awesome. Annular, a combination of annular, or you may hear that same thing called cannular. Throw it all together. And then, what do we have right off of our combustor? What's the very next thing that comes in?
Stator.
Excellent. Stator vanes. What are some other names? Nozzles. Diaphragm.
Inlet guide vanes.
Excellent. So the very first ones are turbine inlet guide vanes or turbine inlet nozzles. And what is important about that part of the engine?
Increases velocity and high engine.
Yes, it does increase velocity, but it is the hottest point in the engine. It is the most important. Josh, gold star.
He's been fighting for that for 3 days.
So, highest temperature is at the turbine inlet guide vanes. Now, what constitutes a stage in the turbine section?
Stator rotor.
have any questions on review? Let me skip ahead. Y'all good back there?
Yeah. We're having fun.
Okay.
What I was supposed to.
So, we kind of stopped, we talked about the main parts of turbines, the turbine portion of a turbine. But there are some unique things about turboprop and turboshaft as opposed to straight through flow turbofan or turbojet. So, if you remember, recall it is a gas turbine engine that delivers power to operate a propeller, is what a turboprop, or operate something other than a propeller like a turboshaft going to the rotor on your helicopter through a transmission. Turboshaft is usually a free turbine setup. We're going to talk about more what that is. Turboprop can be either fixed or free turbine. But typically turboshaft is free turbine. Well, for a fixed turbine, this is an example. It used to be Garrett, TPE 331. Then I think it was Honeywell bought out Garrett and now it's Signal. But they attached the propeller directly through gears to the compressor, which is being driven by the turbine. So attached to the compressor and turbine, and then geared it down using planetary gears, because this is spinning on a PT6 like 30,000 RPM. If you do that to your prop, you're going to destroy it. So significantly geared down to good propeller speed, but now you're getting all kinds of torque. Anyone remember what FG means? Ooh, very good. Force. And in turbines, what force is that? The pilot that's flying an airplane wants all of this force that he can get. Thrust. Overall thrust, yeah. So, gross thrust is what that means. So, prop gross thrust on these is 75 to 95%, so that, and it is go 75 to 95% going to a prop, and the gas or thrust out our exhaust maybe up to 25, typically down around 5%. So really, you're not getting very much thrust from your exhaust on turboprops or turboshaft. And this is a lovely cutaway somebody made of a Garrett TPE 331. So our air comes in. What kind of compressors are these? Centrifugal, and we have two of them. So that's whee, that air goes around this one, whee, into our diffuser, comes onto our reverse flow right there. Turbines are spinning these guys, go into a shaft up to all our gears finally, whoo, turning our prop. Questions on kind of how that all.
Where does the diffuser stop? Where does the combustor start?
So air's coming up, so they have it color coded, like, well, the diffuser should be like right in here. They didn't make that real obvious, but then, like our reverse flow on the PT6, the air is wrapping around and going in all these perforations for burns. A free power turbine, which was, so the very ironic and funny thing, when Case is talking about coming up with a term for free turbine or free power turbine, I had this exact slide up reviewing the PowerPoint when he said that. I was like, that's pretty funny. So I was very excited. So our free turbine wheel, which drives a power output, which is why it's often just abbreviated PT. You'll just see PT, which means power turbine. Drives a power output gearbox rather than a compressor, and is found on turboprop and turboshaft engines. So I have this diagram and then another picture, and you can also see it on the PT6 engine you have. So this is a PT6 engine. So air comes in through our compressors, axial compressors, centrifugal compressor, comes reverse flow through our burner, and hits our compressor turbine, because a compressor turbine is driving compressors. But then there is no mechanical connection from this turbine wheel to that turbine wheel. Nothing in between there except air. So this is accelerating that air so much onto the free turbine blades that that is all that it takes to spin it enough to power our propeller. So that's why it's free, because it is free from the compressor. All of its torque is going to our prop. Yes.
What is the benefit of having a free turbine over a school?
So when you go to start, you're just starting your compressor. You don't need all the energy to start your prop. Do you have questions?
I was just wondering if, like, how much velocity that pressure loss having those two turbines
Right. I don't know amounts of velocity, but however they engineer it, which is brilliant, they figured out blade shape, and you can see significant difference in blade shape and angle from our compressor turbine to our power turbine. Like, very different aerodynamics going on. But all that's designed so that it can extract the energy that it needs. Somebody way smarter than me thought that all up. Here is, it's kind of hard to see on this diagram, but compressor coming up to our burner, going onto our compressor turbine, and then there's no mechanical linkage. Air is going right onto our power turbine, and then out to exhaust. So don't ever do this, but theoretically, you can walk up to a PT6, grab onto the prop. They can start the engine, which is running the compressor turbine, and as they start it up, you can hold that prop, and you won't be hurt. Now, if you let go, now you're going to get amputated, because that's going to kick in. But it's completely no mechanical connection between those two.
And being that there's no mechanical connection when they have a prop set, do they only have to tear down the front of the engine?
Correct. Yes. So yeah, it's going to do nothing to the compressor section. Yeah. Which is another huge advantage. So, anyone recognize what this diagram pictures is? What engine? It is. This is the Allison 250. Yeah. So, I'm going to go through the flow because it's a little wacky. It's pretty cool how they thought this up. So, what kind of compressors do we have in Allison? And centrifugal. Yeah, so if you look, when you do your engines back through, you'll see centrifugal compressors. So both PT6 and Allison use axial flow and then centrifugal flow. Allison is pretty cool because they take compressor discharge air and pipe it the whole way to the back. So you got these big air tubes going the whole way back to our burner. And now air comes back here where our igniter and fuel nozzle are and goes into the combustion chamber. Then it goes out through our in and it's way too much airplane for, like, they don't go through the proper training and they take off like, wrong, and whoop, crash, die. But they are common on helicopters, like our Bell 206 has Allison, yes.
Can you go through which turbine controls the compressor and which one controls the aftertreatment?
Yes, so our N1 are our more high pressure, you could say, because this is the one that's getting immediate heat right off, or energy right off our combustor. That one is going the whole way through to our compressor. And then the next one is our N2, which is this outer one coupled down to the output shaft. Any other questions on?
So how does the combustion not repressurize the tube, discharge tube, the wrong way? Like, does it not create pressure to go back, or is it just so much flow it doesn't matter anyway?
So, what kind of duct?
No, it's a divert.
Right, so building pressure, so we're still having highest pressure.
Isn't the highest pressure right after combustion, after the combustion?
No,
Wait, where is the highest pressure?
Well, at the diffuser, I guess.
Correct. And this one, like this diffuser gets stretched out, so it's still the end of the compressor, but we're stretching it the whole way back to the beginning of the combustion chamber. So we're having high enough pressure here that it's keeping the air flowing.
Is it the expanding air part of the pressure deal, or is that just increased velocity?
Increasing velocity because of design. So it's expanding, but not more pressure, because rather than expanding and having nowhere to go, all the ducts are transferring that energy into velocity. Well, and the rotor and stators are extracting that energy as soon as it's coming off our combustor. So we're extracting energy, shoving pressure, so that's keeping it going. Yes.
Which part of that's the diffuser?
So it would be kind of this whole thing, but really, on this diagram anyway, this is where it's widening out the most. So Allison's is a little wacky. On PT6, it's obvious. It's like, okay, right here's our nice little short little diffuser. Where the Allison, they're taking it the whole way from here to there. So kind of a whole diffuser tube, or you could say diffuser section here.
and then the smaller section of blue air going forward for cooling.
Through here? Yes. Yeah. Around that case. Good question. Oh, this is a nice cutaway. So now it's flip-flop because we have our compressor up here. But you can see the tubes, and we have vanes directing the air around that turn and widening as they get back here to our burner can and then coming forward. So it's like inside, front, going towards the front, and whoop, out the side. Very confused airflow, but it works very well. All right. Any questions on turbine, turboprops, or turbo shaft?
So there, the cutaway, just need the red on the exhaust, like where the main shaft is.
Right.
Is there air in there or fluid?
This is all air. Because this
Right,
is.
but that shroud would keep that shaft isolated.
So. Wait. Oh, like to have a.
Right, is there
Yes.
any cooling in there or?
So we do have, like, right through here, that gap, we have cooling air going.
Right, that's on the outside, but like inside the turbines.
In here, it would
In
just.
the shaft to the right of it. Yeah, what's in there?
Right.
Nothing.
Oh, this is cutaway. So this would.
Correct, so it's sealed.
Correct.
So it's
Yes.
just
But
air.
probably maybe back in here, we might take some and vent it around there. Somewhere there would be cooling going cone, and then the tail cone around it, and extension of that is a tailpipe. The exhaust section is located directly behind the turbine section and consists in most cases of a convergent exhaust outer cone and an inner tail cone. The tail cone shape acts to form a diffuser. So our initial tail cone, you can see that is going from smaller to larger, so that's a diffuser. And then the exhaust cone, we're going to talk about this, is convergent. So we're doing all the best we can to get the best energy and thrust out of that exhaust. The exhaust cone is the terminating component of many engines as delivered by the engine manufacturer. So, like on the PT6, that stops right here. So the exhaust nozzles that come out all fancy on the Kodiak or on the King Air, that's going to be a airframe component.
Question.
Yeah.
So the exhaust is convergent?
So initially, like right here is the end of our turbine.
So it diverges and then converges?
Correct. And we're going to
So
go into all of that.
the diffuser section it's referencing, where's that on the exhaust?
Is
Right.
right there, because as soon as it passes that, then we start to go converge.
So diffusing is always referencing diverging duct.
Correct. It is. Yeah. Good clarification. Exhaust gas temperatures. I think you were worrying about this just this morning. I wasn't overhearing too much, a little bit, when I heard my name. Like, so, this is the temperature taken at the turbine exit, and is very vital cockpit indication for starting and engine operation. Anyone want to guess average, maybe Case told you, exhaust temperature on a turbine? Well, excellent. 600 to 1,000 Celsius, depending on the turbine. Anyone know typical piston engine?
1400 Fahrenheit?
About 7 to 800 Celsius. So that doesn't, yeah. I can't convert in my head. But cooler on piston, much hotter. Roughly, again, it depends what you're comparing on turbine. But what do you think these thingamajiggies are? Excellent. Thermocouples. They'll put a thermocouple ring around your exhaust where you want to take your exhaust gas temperature. You can have analog dial or nice digital readouts. And not every turbine engine will have EGT gauge. We're going to talk about yeah, that picture will work. So sometimes, like on a lot of PT6 engine aircraft like the King Air, we don't have exhaust gas temperature probes. We have inter-turbine temperature probes. So on the PT6, right in between our turbines, we have our thermocouple ring in here, which the harness for that has got to come up between our burner, and if the thermocouple goes out, it is a nightmare to replace that. So, but it's in a really good place to get the inter-turbine temperatures. What would and we're wanting to know what's going on back here further in the engine for performance. What would TOT be for? Turbine outlet temperature. So you might see TOT or EGT, exhaust gas temperature. And yeah, ITT is what we're going to be looking at on the Kinger when we do engine runs for inter-turbine temp. So on this one, you can see we've got divergent with this outer cone, and especially this tail cone here is creating a divergent duct. But then as we come down, right about in here, it is convergent, because we want all of the velocity we can get out the back of that exhaust. So starting divergent and then coming convergent. And the tail cone is the main component, is creating the divergent duct. Yes.
What did Brian ask earlier? What from like the immediate exit of the turbine to that little notch looking thing? Is that, what did you say? That's always convergent or divergent?
That will, and generally speaking, now when you get to supersonic stuff, generally speaking, it'll be convergent. And this is, in different diagrams are going to show a little different. So this one is more obvious with this tail cone to the side is becoming more divergent.
Then it says divergent up to line.
Right.
Is this like the diffuser part of the exhaust immediately after? And then it goes divergent until that blue line?
Yes, because that's about where this tail cone ends. So now all air is coming up, but this outer exhaust nozzle is, since that's the end of that, convergent.
So is a lot of times it's convergent, divergent, convergent?
Most common is divergent, convergent.
So the whole divergent section is the diffuser then?
They don't really use the term diffuser on exhaust, even though that is what it is acting as. Yes, from the end of your turbine here, because your exhaust cone is coming out and creating that divergent duct.
Divergent ducts have diffusers, convergent ducts have confusers.
That's awesome. My boggle part of that for a second. That was great. Anyone not confused? So yeah, generally it'll be divergent because of the cone, and then since that ends, then a nozzle shape takes over of convergent.
Okay.
Is there a reason the blue line is more to the right of the end of the column?
I think the illustrator was like, all right, right there, right there. Oh, bummer. Now there could be with the airflow, like maybe it's still pressure, and it's only at this point that, oh wait, now I'm converting more to velocity. That could be part of it too. But some of these diagrams you have to be careful not to read too much into, because some have better points, others have better points than other stuff. Any other questions on this? We're going to dive into some supersonic exhaust nozzles that get even more exciting. Could anyone remember what choked airflow is, or kind converging duct. Well, I was like, oh no, what if they remember everything? And then I have this slide in here. Excellent. So, an airflow condition from a convergent shaped nozzle where the gas is traveling at the speed of sound, but it cannot be further accelerated. Any increase in internal pressure will pass out the nozzle in the form of pressure. I have another graph coming up, but basically we're accelerating, so this should be extended a little bit, but have a convergent nozzle and accelerating air until it reaches the speed of sound, forms a shock wave, boom. But what happens with a convergent nozzle when our air is at the speed of sound? Exactly. So now the velocity would be wanting to decrease, pressure would be wanting to increase, so it just holds that. And the reason they do that is to get more pressure out the back of that nozzle. So a ton of engineering goes into how much is it converging, how long do you make it, so you have that shock wave happening at the end of your converging section.
So is that why fighter jets have like an adjustable nozzle? Like they can open up?
Not as much for choked airflow, but that can have, we're gonna talk about that. But, cause they go beyond, cause they have divergent, convergent, so they want actually supersonic exhaust rather than just pressure. But this is used more on like a turbofan, because this is a good example, on some airliners where they want all the pressure, but they're not going to have a supersonic exhaust. So here is the diagrams. When gas initially flows down a convergent duct, which is our converging duct, the shape accelerates the gas, because subsonic, we're accelerating our velocity. As more and more mass of air flows, so we're shoving more air, flows downstream, the duct starts to constrict the flow. At the point of Mach 1, or speed of sound, the walls of the duct are constricting with a force equal to the air's axial flow force. So we have axial force and force from the sides going on and equalizing, and that helps stabilize it at Mach 1 or the speed of sound. So this shows it really falling off if we don't have a choke nozzle. But if we have a choke nozzle, we get a lot more energy coming out of the back of that nozzle. Questions on that? And you won't be super deeply questioned on this stuff. Just know that's there and it comes up to the speed of sound, and then that's where it stays. And they do it to get more pressure. More pressure and more energy. And this is a nice diagram. We have our exhaust cone, tailpipe, and then our exhaust nozzle converging at the end to get the speed velocity that we need. This is also, if you go to page 3-26, there's some of the diagrams you were looking at. And also shows figure 3 lungs. So they'll make these divergent nozzles to make sure we're not getting too much velocity out of there. And some will have a scalloped shaped outer perimeter, and that is for noise suppression. We'll talk about noise suppression in a little bit. So divergent, often on rotorcraft. So to nullify or lessen thrust, to enhance hover. Then, alright, that's break time. I was getting all excited about afterburner. Come back at 12:30 for afterburners.
What's up? You guys wanna go check and see if the guy's on? Did she say she started at 10:30? Started at 11:30?
Right, what kind of test did you take?
Huh?
What kind of test?
Some random guy.
What kind of test did you take?
I don't know. I don't know if it's general or airframe. Could be power plant.
Could be.
Oh, oh, like
Oh, I actually know nothing about driving, so I don't know. I guess if you get a drone license, it would be like airspace.
Probably. Probably more than that.
Yeah, regulated. That's why we're not.
Like from airports.
Yes.
Or like capitals of the nation. No big deal.
Okay. Did you tell her I'm okay if she comes in and just signals you guys when
Okay.
she's ready?
Let her know. We're just gonna do this quick. Okay. Watch. Stressing? You just spent the last 4 months preparing.
That's right.
Good.
And if like what happened to me, I think I forget it was general airframe. I got in there and like the first 4 questions I was like, oh my word, I don't know. But I just went through and till I found one. Man, I knew this, and then like my confidence built. And then I came back like, oh yeah, I knew that.
Get the swing. Yeah, your first several.
Yeah.
Dude. You're off my left. No. Ah.
Okay.
Leader. That's actually great. What? What?
I thought meerkat. I know.
Go join him, Barb. Let's see it.
I can do about
Oh,
half a second.
yeah, I can just about get in the position.
Yeah.
That's, yeah.
really depends, like,
Howard was the discharge.
Yeah.
At the hallway?
She was 16, or did
Hey, or
he
40.
show up
How
when
far down do I?
he was 40?
Should be 90 degrees, but
Yeah, Barb.
Oh my Barb.
Christina, now you have to.
Hey, I tried a long time ago.
Come on,
I was like,
Christina.
yep, I greatly respect you.
Is anyone counting?
Sam's got it.
Whoa.
I mean, mine.
Yours.
Holy, come
I
on.
think he noted it's up.
30
Barb,
seconds.
you sure you're gonna be able to walk the next day?
30 seconds, 30
You
seconds.
sure you can walk tomorrow?
Are you under your time?
Sure.
I have,
This is.
you know, I do more at home. You know, outside work and whatever. So, yeah. However,
There you go, Barb. There's 30 seconds.
Whoa, that's way better than. Now I feel like a wimp.
yeah, but it certainly,
You can feel it.
yeah,
It's gonna sound like a big sheet of sheet metal.
Yes. Cool.
You guys just need to add weight now, like put your backpacks on your.
Ooh.
Sydney, you can do that if you want.
yeah.
Yeah, once you get up to 7 minutes to meet, you can do that.
Fair enough. No, but then you can reduce your time but add weight.
Oh.
Or you can just end it with jump squats.
Ooh.
Oh, my goodness.
That's a
You know what?
good, that's a great idea.
That would hurt so much.
Jump
Why are yours
down,
up?
squat, and then you jump on the way up.
Thing I
Ow.
do.
Ow.
Don't ask.
It's not a thing. It's just is.
I'll try to do 2. Let's see if I can. As soon as this is over.
Don't hurt yourself.
How long?
I might just
how long?
collapse.
You don't say. If you say it, just makes it that much harder.
Oh, okay. Well, I
makes
didn't
it
know how long I
incredibly
was gonna
harder.
have to stand here.
That's
Wait for him to.
fine. You already saw the watch, so.
Stop looking,
I'm
dude.
okay with knowing.
Plug your ears.
Look yours.
1 minute 30 left.
Okay.
Or I'll go get my stellar.
See, it suddenly got harder.
Then I'll
Just
be
because
back.
of that.
You should
Hey,
have
were
said.
you already looking?
But the time's already going down. It's like way less than that already.
Yep.
See, you just say 30 seconds for a minute and 30 seconds.
Okay. Let me look at the phone. This is what makes the time go by.
They're starting to, they'll start, they're wiggling. Wiggling.
Commentary really helped.
Sam, you're starting to look like Batman.
Commentary really helps now.
You got a nice scowl going on.
So I like how Tim and Sydney both had things on adding weight, but neither of you are doing it.
Hey,
So at least Barb did it.
I've done it. I can do it, not as long as they can. But I can heckle them all I want, and it doesn't hurt me in any way. So,
They
Yeah.
hurt you.
they might.
That was 7:15.
Oh my word.
Well,
Maybe
do
we
it.
stretch it out.
When you tear a ligament, I'm not taking you to the hospital.
Oh, that looks so painful.
He was doing jump squats.
I just wanted to
He
show Barb.
got 2 jump squats.
additional. They might do 15 to 20%, still get good thrust augmentation, but now you're not burning through your fuel like crazy. So today, that is why they're just augmenting the thrust or helping it. So that's why a CV, convergent divergent tailpipe, is called thrust augmenter. That terminology more common than afterburner. So know that for testing for prepware, the thrust augmenter is more common that you'll see, but it means afterburner. And what it is, they have a fuel manifold and then a flame holder to control that flame installed in the tailpipe. And we're going to talk more about those in exhaust systems class, but that's, and I have really cool videos in exhaust systems class. So you have to wait for that. And go to the Battle Creek Air Show.
So is that basically just another, like a second combustion chamber? Or no?
Kind of. I mean, it's hot enough where we get more fuel, it ignites, but it's not considered a combustion chamber.
Right.
Even though we're burning leftover and more
Is
fuel.
that unburnt fuel at that point, or am I system?
So there is unburnt fuel, yes, and we also can add fuel. So it's both of those, yeah. And that would depend on the engine, like if we're just went a little bit, we won't be dumping as much fuel, but on the military aircraft that I built, use them on they can.
So, if you have an afterburner in use, how, in relation to everything else, how hot is it? Is that become the new hottest point in the engine at the tail?
That's an excellent question.
So, I mean, obviously you're dumping more
Right.
fuel here than
Right.
you would earlier on, but it's less contained.
Right, because it's less concentrated, I'm thinking it would still be at the inlet of the turbine. That is a fabulous question for Kirk. Because I would research it, but that'd be cool, like, Kirk might. My thinking is that because we're getting velocity, it won't be as hot.
The reason I say that is we had a MiG-17 that burned out its tail because they have to put fuel.
Oh no, well, if things go wrong, you can 100% exceed temperature, absolutely. But if everything we're operating correctly, I don't know. I'm thinking it shouldn't be. Or within the engine proper, inlet to the turbine, where this is now or after all our operating components, so do they not include that when they say within the engine? That could be the other caveat.
Is there igniters on there then? Or that's just it's hot enough?
It's hot enough.
Hot, okay.
Yep. Toasty. Yes, Josh?
An afterburner or something that the pilot just turns on when he wants to go faster, or is that
Right.
when you put the
Or
throttle forward
whatever
in the
performance.
after?
It will be pilot controlled.
Is it like another switch, do you know, or is it like just in the throttle
airflows down by up to 15% to optimize hot exhaust flow and performance during takeoff, climb, and cruise operation. So we are going to talk a whole lot more about variable exhaust nozzles on supersonic aircraft and exhaust systems. We go into a lot more depth. But just be aware they're coming out with some for subsonic aircraft. But thrust reversers, we will talk about airliners. Airliners powered by turbojets and turbofans. Most commuter aircraft and an increasing number of business jets are equipped with engine thrust reversers. And they aid in braking and directional control during normal landing to reduce brake maintenance. And also during emergency landings or rejected takeoffs throughout the thrust reversers. And they can be used to back an aircraft out of a parking spot, called power back operation. Do you think they do that very often, and why or why not?
Dangerous,
And why?
because you're, the can't get behind you, also.
That's good.
You're directing the airflow down and almost forward,
Exactly.
so everything in front's gonna get,
And what about the engine itself?
I don't like that.
Exactly what Gavin said. It's going to start sucking up its own exhaust, and that is not good for it. Now you have hot exhaust coming in your inlet, and all of the whatever's in the ground and the air, it's going to throw gravel and who knows what up into its inlet. So, not used very often. So, a thrust reverser is a device attached to a turbine engine tailpipe to reverse the exhaust gas flow. That's one style. We have two types. So we can use aerodynamic blockage. I'll have pictures of them. Aerodynamic blockage is sometimes called cascade, and you're going to see why that is, or egg crate reversers. And then, like on our beach jet, we can have mechanical blockage, or clamshell, or called target, and you're going to see why it's called that. Come on, picture. One more. So a common method for operating both types is a pneumatic actuating system powered by compressor discharge pressure. Other types use hydraulic. Hydraulic is what is most common nowadays. That's how our beach jet does it, is through hydraulics. So here we have the bucket or clamshell, because normally these are, so it would be coming together right through there. They should have a line through there. They would be stowed down along the sides of the exhaust, and then when they're deployed, they come out and BAM! So whenever you're testing thrust reversers, make sure everything's cleared out around your engines. Stay back, or you get pinch of a lifetime. And then cold stream or locker system, or the aerodynamic locking. So this is internal, and I have a video. Part of the side will slide back, and there's some vanes that come down. These are on turbofans, so just our fan air is blocked internally, and then as these here would normally be closed in flight, but when you deploy thrust reverser, this slides open, and vanes come down and block all around for the engine, block the fan airflow to allow the air to come out the side. It looks like, so cascade is the other name because here it's operating. So normally this would be slid back solid to here, but kind of opens up this opening, and inside the engine, so here's our forward engine, fan air flowing, core air flowing, and when we deploy the cascade thrust reverser, that blocks just the fan air, and the side opens up so that fan air can flow out and be directed forward. Zach?
What about the ones that things like A319s have them where like 4 like separate ones come out?
Like-
What is those like classified as?
They come out like that?
Yeah.
That'd be like a bucket for clamshell. Or are they on more on the side?
Yeah, there's like, there are 4 in there.
Yes, yes. So you can have a combination of this stuff.
Is that what it is?
Yeah, I would think so. I'd have to look at it for sure, but it's sort of mechanically blocking it, but also I would think inside they're redirecting the fan air as well. So you can do it all.
Isaac sent us a picture of the previous slide.
So this one is just coming out the very back of the engine. Oh yeah, there was this at the bottom.
Yeah,
Yes,
the 319
yep.
in the middle, yeah.
Yep. So I would think this is somewhat of a combination, although it would be more, it's in the side, it's not coming out the back. So there's cascade vanes inside. So rather than sliding back the cowl, they're just opening up sections. Yeah. Thanks, Isaac. Oh no! Okay, we'll show the video. So you can see right here. Directed forward with aerodynamics inside. When these babies close, don't have anything in there. Very important. And all the different styles of thrust reversers are high maintenance items because there's lots of moving parts and hydraulic actuating things going on.
So is there a seal between those two valves?
There would be some kind of, I mean, you can see how thick this wall is. And we have this part here coming out a little bit. So yes, there would definitely be ways to seal that because you don't want, when you're flying, you don't want any fan air.
Is there a certain power level that
Yes, I think we're going to, oh my goodness. You get a gold star because that's my very next slide.
that's
Yeah, that's cool.
Everyone's gonna hire you.
So, kind of two numbers. So it can provide approximately 20% of braking force. So huge help to save your brakes under normal runway conditions. And it's capable of producing 35 to 50% of the rated thrust in reverse. So what happens is, and this is similar to our beach jet, you have to, the aircraft has to slow down because there's all kinds of sensors that will not allow you to deploy the thrust reversers at higher speeds. And to weight on wheels, all that stuff. Aircraft slows approximately 80 knots. Power is reduced back to reverse idle power. And then you reach forward, grab the thrust reverser levers, pull them out, that deploy the thrust reversers, and then the whole thing you can shove forward to get more thrust in reverse. And slow down.
So, sorry, you just said it. Do they usually use them for braking? Or is it one of those emergency stuff?
It depends. It depends on the aircraft, the design, where they're landing, runway length, runway conditions. If in my a good filter, but not good for your engine. Normal procedure for thrust reverser is to select reverse after touchdown at ground idle speed, and then reapply power to about 75% into. What is into?
Second station.
Second stage compressor. Noise suppression, we're going to talk also more about this in exhaust class, but noise is best defined as, for engine purposes, unwanted sound. So, I like that definition. Because it can be irritating and harmful. Oh, here's a free story. So, a couple nights ago, I was trying to sleep like 11:30, and some unkind, unthoughtful person was tearing around Ionia. I don't know what it was, if it was a dirt bike or a motorcycle. Hopefully it wasn't a
Might have been a dune buggy.
That's what I need to teach it. At 11:30 at night?
Maybe.
At extremely loud volume? Like it was
Might
like...
have been straight bike, yes.
Did the police chase you?
No, I did not get chased.
Okay, because I heard it going.
There was a Hellcat that did get chased the other night though, and he kept running.
I heard it going.
He did not stop.
Like this was obnoxiously loud. And then I was like, so I started, I was like, Lord, I need sleep. Please make some police officer chase him. And not a couple seconds later, I heard sirens and yes, go get him. And then I heard the bad dude even more accelerating, and then I tuned into the police channel. Yeah, he's headed west in Washington Street. It's like, oh boy, go get him. And then he turned, and then I didn't hear the bad dude anymore, and the sirens got quieter, and then suspect apprehended.
Oh.
And then I was like,
You gotta be quicker than that, man.
I was like, I hope that wasn't a SMAC student. No, you guys wouldn't do that. Anyway, sorry, that was a total rabbit trail. Noise suppression. Okay. So, focus back to turbines. Sound level of the average business jet or airliner taking off, as heard by people at the airport, would it be about 90 to 100 decibels, which damages hearing. Noise from the exhaust is a very low frequency. So, do you, without reading too far along, is low frequency or high frequency travel further? Low frequency travels further. So, like a ship's foghorn. So, they tend to linger at a relatively high volume. So, what we do is we do things to raise the frequency, like increase the perimeter of the exhaust stream and provide more, which does, and there's other ways too, provide more cold and hot air mixing. So it'll look something like this. Increase the perimeter, mix the cold and the hot air, and that raises the frequency of sound so it dissipates more quickly. And what's causing all that noise is we have turbulence coming out of here, a shear edge, and all that like boom, making all that noise.
Higher bypass also.
Yes, if you have more cooling air coming out of your fan and you mix that exhaust, that's the hot and the cold changing all of this stuff going on off the bat, and that helps suppress the noise, yes.
They're not destroying the truss.
Not, well, not as much as what you might think. Now, it does have some effect because you wouldn't see that on like military jets or stuff, but I don't think it's super common anymore. And we'll talk more about ways to do noise suppression in exhaust make it vulnerable to combustion. So unlike most structural metals, titanium ignites at a lower temperature than it melts. So rather than melting and then catching fire, it'll catch fire first and then melt, which is unfortunate. And it has lower conductivity of heat, so it's gonna, not be conducting heat as well. Hot section materials. We have a variety of high strength to weight materials, and they are called super alloys because they're so cool or hot. They have a maximum temperature limit of 2,000 degrees Fahrenheit when not cooled, and like the turbine blades I was showing yesterday that have those cooling holes, they can go up to 2,600 degrees Fahrenheit if they're cooled internally. Superalloys were developed for use in high temperature areas where oxidation resistance is needed. What is oxidation? Corrosion. And where high thermal, tensile, and vibratory stresses are present. So you're having high heat, you've got tension going on, and everything's vibrating because it's spinning. Superalloys are complex mixtures of many critical metals, so you can have nickel, chromium, cobalt, titanium, tungsten, carbon, and other stuff. Not stuff you need to memorize, just be aware. And no, it's very critical to choose a proper metal for high temperature area. Ceramic and aluminum alloy thermal barrier coating of superalloy parts and some titanium parts are also processes which give high surface strength and resistance to corrosion. So if we want to use titanium, because it's so light, even though it gets dinged up easier, we can coat it with some ceramic and aluminum alloys. And the coatings, generally referred to as plasma sprays, they're applied under high heat and they kind of melt into the surface of the base metal. So now we've got lightweight, heat resistant, and resistant to being damaged. Again, all this stuff, super expensive. Turbines are expensive machines, but they're so cool. Any questions on what we've covered so far? Okay. We are going to go into some accessory stuff for a little bit. If you need, don't leave the classroom, but if you need to stand up and get your brain re-engaged, that'll take me a minute to switch my PowerPoint, so feel free to stand up, stretch.
I just need coffee.
No fighting. Stand up. Oh. All right, I already got to my PowerPoint. Sorry. Computer. Okay. You are welcome to stay standing, but if you could please be quiet because you're creating noise, which is what. Hey! Oh! Good time? Sweet. Good luck.
Later, ladies. Whoa, easy.
Okay, so moving into the next section of lecture, which is, so we've covered, you guys doing so good, pay attention, some of you. We've covered our inlet, we've covered our compressor, types of compressors, diffusers, our combustion section, turbines, and exhaust. So what is left? Accessories. And gearbox on turbine. So we're going to do a little bit today and then do some lectures next week. We're going to be covering lubrication, fuel, drive external gearbox is where it all starts. A secondary function of many gearboxes, like on the PT6, is to provide a collection point for the scavenged oil before being pumped back into the oil tank. So on this one, here is an accessory gearbox, or here we have it on the bottom of the engine, our accessory gearbox. And what kind of engine do you think this is? Turbofan. Good. What does it say on it? It doesn't. But yes, this is a turboprop. We got a shaft out here, and our gearbox is on the back. Now, Zach, turbofan or turbojet, you can't put your gearbox on the back because that's where all your thrust is coming out. So then you move it to the bottom or somewhere else on the engine. Accessory drive gearbox, you may see it abbreviated ADG, accessory drive gearbox. On some installations, an auxiliary gearbox is employed to drive the main gearbox. So you have your main accessory drive, and then you can have another auxiliary drive. So here we have our main gearbox, and then a shaft going to our intermediate or auxiliary gearbox. This arrangement allows the gearbox to be placed so that the envelope size or space of the engine can be kept to a minimum. So depending what they're using this engine for, depending what other accessories, instead of having everything hanging off right here, they can kind of spread it out along the engine. My word. Here we go. So you may see it called main gearbox, the main accessory drive gearbox. And is often driven by a radial shaft that meshes with a bevel gear driven by a main rotor shaft. So we got all kinds of things coming out. We got a drive shaft for our auxiliary gearbox, oil tubes, our main gearbox down here. So you can have all kinds of ways of connecting your auxiliary gearboxes to your main gearbox. Your main gearbox is going to provide a mounting space for engine accessories like a fuel pump, fuel control, oil pump, starter, hydraulic pump, generator, whatever fun things you want your engine to be driving. And just to know, tuck away, the fuel pump and fuel control are very often combined together, especially on the PT6. So this, you can kind of see how they're representing the main gearbox to the auxiliary gearbox. And this is what it can look at, just one example from the outside. And here we have bevel gears coming down to a shaft, some more radial bevel gears going out to all of our alternator, fuel pump, all these gears are driving and accessories. And we're going to hop over, this is a PT6 that I'm most familiar with. So I got on the back our gearbox, and this also acts as a oil sump. So we have all our scavenged oil pumps being driven in here. And we have the gearbox input gear shaft driving on these guys. So oil scavenge, some more oil scavenge stuff, fuel pump, and starter generator. So all of those gears need to be meshing properly to do their job. Lubrication system. So if you go in your textbook to page 6, chapter 6-18, this is where it talks about lubrication systems. pressure changes with, well, yes, pressure changes with RPM. So more RPM, more pressure. And it is a system of choice when the bearings, vent cavities, contain high pressure. So all your bearings in your shaft, if you have high pressures on your labyrinth seals, you want a full flow system. Primary is something to know. Primary function of lubrication system is to supply oil to the various parts within the engine that are subjected to friction loads. So all your shaft, all the bearings in your shafts, from engine rotation and heat loads from the gas pack. Oil is supplied under pressure along the main rotor shaft and to the gearboxes to reduce friction, to cool, and to clean. So those are three things to keep in mind. They're reducing friction, cooling things, and cleaning things. And then returned by the scavenging system to the oil storage tank where it's stored and reused again and again and again. Something to know, this one doesn't have it, but the PT6 that's on the stand with part of the prop on it, you can look at that and you'll see the scavenge lines, the return lines of oil are larger than our pressure lines going out to our pump hose. Why do you think that would be? It's expanding because of the heat. And we're scavenging, we're cleaning, so we might have some gunk coming back. Particulates, such a good word. So here, we've got pressure line little, and then a larger scavenge line, and this is from the Gulfstream 550. We also, on our turbine fuel oil systems, will have magnetic chip detectors. Did you learn at all about magnetic chip detectors?
Yes.
And what did you learn about them?
They're finicky and they go off sometimes randomly, and they're good safety.
And how do they work?
Right, sections, it connects the circuit.
Excellent.
Yeah, that
So we've got two magnetic poles, and when metal whoop, goes across those, completes a circuit and says, uh-oh, got a problem. When we do our engine run-ups on the King Air, we're going to be looking for warning lights from our chip detector. So on the PT6, we'll have, here's one up here, and the one on our accessory gearbox, I think is taken off, but you could have one on our gearbox up here and one back there to detect any chips in our engine. And this is definitely an inspection item. Any particles must be analyzed to know where they came from, what might be breaking down. Yeah.
Are they usually gonna be found on the bottom of things where particles are gonna kind of float around?
Yeah. Yep. They will. And most nowadays, hopefully, but this is something super important to read the manual carefully to know if it has it. Most of them will have a self-closing valve, so you can remove them without draining the oil. But some old engines might not. So make sure you don't think you're going to just do a quick little removal and now you got problems. So read the manual to know if it has self-closing valve.
You said, all the particles have to be inspected and analyzed?
They do.
Do you have to send those in to do that?
Yes. I don't know if a shop could get certified to do the analyzing, but typically you would send it to the facility that has all the equipment to do that.
So chip, does it catch? Do you catch the particles detector?
Yes, it'll be like, I think the one out there you can see better where it's at in the system. That it'll kind of attract 500 flight hours, it can be plus or minus 50, but can't exceed 1,000, so you can't keep stretching and stretching it. It has to be every 500. So that's how the frequency that these chip detectors are inspected. And then you have C and D checks that are more heavy maintenance stuff.
We have the 400 so.
I don't even know what to say. Some principles of engine lubrication. So the cool thing about turbines is they are not oil consumers. The oil consumption is very low in gas turbine engines compared to pistons, which gobble up oil. And that accounts for a relatively small bulk oil storage tank. So compared to a piston, we have really small storage tanks on our turbine engines. So in theory, a lubricating fluid will fill all surface irregularities. So it fills that in, makes it smooth by providing an oil film that just slides against each other and prevents metal to metal contact. So here you go. Here's your, you need to know this. Primary purpose of a lubricant is to reduce friction between moving parts. Secondary purpose of engine lubricant is to act as a cushion between metal parts to cool and to clean. So if we have like bearing on a shaft, we got to reduce the friction and make a nice cushion between that metal and keep it cool, keep it clean. The oil circulates through the shortened it so we can, but I'm trying to push through so we can get finished with lecture and then get lab time.
You have an estimation plan for me?
Put that one down.
3 hours.
Note down that.
I think 20 minutes is my actual. Corbin's like, I'm done. I can't take it anymore.
How feel it, Dan? Patient wears out in the morning. Okay.
That makes sense. We should coordinate better, not
We're here
give
now,
you
it's
like
time to go.
8 hours of lecturing.
I have one twice today.
Are you serious? Dude, he's on a hot streak. 3 gold stars. And 2 minesweepers. Yeah, man. Could the day get any better?
Yeah, I got it.
3 minesweepers.
Yeah.
I'm going to get
Double.
double.
And the day's coming after you get 4 gold stars.
Wait, I can't open the cameras?
Oh no, he's testing.
Wow, Dan.
There's a couple of guys in the
Why you
wall
gotta
shop.
take pictures and
Uh-oh. What do they do?
Probably welding.
That, can you grab
Slides.
people that try to do something they're not supposed to be doing?
Your work organized on
It does. Yeah, especially like the last one.
People get too comfortable.
Yeah. What are you going to do?
Yeah, we don't got you.
So much makeup time, you won't have time for the next 30 years to do anything else.
You awake there?
What's the authority?
That's right. Alright. You want a recommendation letter now, do you? Well,
Yeah.
I will give you a recommendation letter.
Not saying which way you're recommending.
To McDonald's, it would be an excellent burger flipper.
I advise you not to hire this person.
Yes.
I recommend
I
not.
recommend that you do not. Okay, we need to keep moving, so the people that aren't in here, they're going to be missing vital information to their own detriment. So requirements of turbine engine lubricants. What must our turbines have? So, turbines use a lot less oil, but they are picky. They want it to be very excellent. So, Joey gets to figure out what he missed that he would fail a final if he doesn't know.
Ooh.
Nobody tell him, he has to figure it out.
Can I guess?
I'll give it to Zach.
I missed like 30. Synthetic.
I'll give it to Zach because he went to get people.
Oh, you want?
So, gas turbine engine oil must have high enough viscosity. What is viscosity?
Ability to flow.
Excellent ability to flow. Enough viscosity or flowability for good load carrying ability, but it must be, so it has to be thick enough or viscous enough to carry loads, but sufficient low viscosity, so thin enough to provide good flowability. So you need that balance to carry load and to flow. Because of these requirements, synthetic, so this is key to know, turbines take only synthetic oil rather than petroleum-based lubricants. So, and 2380 is a common kind of turbine oil. So, what is volatility? Unstable, yes, or ignite, ability to vaporize, very good. So, also of note, so turbine engine oils, they are not by SAE numbers. There's only 3 types of manufacturers that make the correct qualified turbine engine oil. So that's where that number on the previous slide came from. So it must have low volatility to minimize evaporation at high altitudes, anti-foaming quality for more positive lubrication. You don't want it to just be foaming up. Anyone know what the negative 60 degrees Fahrenheit to 400 degrees Fahrenheit, so that you don't have to preheat your engine. You want your oil to be good and flowing at cold temperatures. So on typical turbines, they do not need a preheater unless it's negative 40 Fahrenheit, which is super helpful. Requirements of, oops, I saw one here. This one, high viscosity index, an indication of how well the oil will tend to retain its viscosity when heated. So as it heats up, you don't want it to get too flowy. You want it to still maintain viscosity needed to form a cushion. Any questions on those? Now, requirements of lubrication systems. The word oil must be stenciled in the area of the oil tank filler opening, so people don't come and dump fuel or something else in there. Must say oil. It must have a means must be provided where it is impossible to inadvertently fill the oil tank expansion space. We're going to look at a diagram of how it does that, so you can't completely fill your expansion space, because if you would, it has nowhere else to expand. And with that, your oil tank must have an expansion space of at least 10%. There must be an oil scupper provided to carry spilled oil to a drain point. So you have to have a drain force to drain oil. And your oil filter, which I've talked about in the lubrication class, must be a type through which all of the system oil flows. So all of your oil must be filtered. Servicing turbine engine oil is a little different than recips. Generally required after the terminating flight of the day. So end of the day, putting the airplane in the hangar, or whenever the flight crew requests it. So for turbines, you want to, the best time you need to check oil quantity just after engine shutdown while the oil is still warm to get the most accurate reading. Now, you're going to check it before you start to make sure something crazy didn't happen and you lost all your oil. But when you want to get the most accurate reading, you need to check it about 5 to 30 minutes after shutdown. They most never get topped off, so you never fill it to full. Never open a cap on a hot engine. And
But it says, monitor the oil is still warm.
right, it's still warm, but you'd be surprised. So you'll see when we do King Air how quickly the engine cools down. So if your engine is super hot and you go up to it, don't be opening that cap. Many times caps are safety wired to keep pilots from messing with it.
Then how do you check it?
Now, so I believe, so this may be on engines where your fill cap is separate from your dipstick, is what makes, yes. Although, here we go. Here, this was a picture of, so our tank, and then we have additional expansion space that the oil wouldn't be sitting in, but it can expand into that space if it's really frothing up. So this is a PT6 diagram, and I don't want to go into too much detail, but you can see this is our center shaft. We have all kinds of bearings through here that must be lubricated. So this is the back side of our engine, our pressure, and we'll talk in fuel class about our fuel heater, so our oil can heat up our fuel so it doesn't get ice in. Pressurized oil getting sprayed onto each one of our bearings, and we also use oil for our propeller, and then it drips down into here. We have two larger scavenge line lines, coming back in all kinds of scavenge pumps to put that oil to where it belongs, and also send it up here. And this is a little splash plate that aerates the oil or gets the bubbles out so it can settle back down into the tank and get sent out again. On the PT6, I want to show you the dipstick. So, very important, your dipstick must be latched. If you just drop it in there and don't turn it and latch it, it's gonna spew oil out when it's running. But PT6 is unique. It has on here. Let's see if, so you can kind of see max cold, max hot, but then down here we have 3. See if we can start, right there's 2 up here, 3, and 4. So did they label this backwards?
4 quarts?
Speaking of that, I know. Ah, have you worked on Kodiak much? Okay. Leo, did you flip it?
How much you gotta add?
That's actually kind of way of thinking about it. Would that work? So what it is, it's how many you're down. So if it's, so up here we have 2, so that means we're 2 quarts down. If we're at 3, that means we're 3 quarts down. And at 4, we're 4 quarts down. So, and you wouldn't add it full, you would just add it. Normally on PT6s, they run at 2 quarts down. So that's where we like it.
So it means you don't top it off then?
Correct. Yeah, so typically keep it about at 2.
So you might need to fill it up, but topping off means
Yeah.
fill water up to max.
Correct. Because yeah, it has like 2s down there, and then up here is max. So you would typically just keep it filled to 2. You wouldn't fill it up to the max. On our King Air, our left engine is right about at 2. Our right runs at about 3.5 down. Although it's up to like 3.25 down when it's warm when you're supposed to check it. So that's what's typical for our King Air. It's a little bit old. Normally you run PT6 is 2 down. And come back to life computer. I think in just a short time. Here we have it up there. Oh yeah. Oh, no, that's it. We will do fuel next week. So, would you like me to continue lecture? I can.
Yeah.
He's silly. So, I was going to show you the schedule. But, oh, we came too late. Oh wait, here we go. So if y'all can pay attention so you know where you belong. You belong to G. So, yesterday, group 10, Austin and John, did you complete your boroscope? Excellent. And Samuel, Brian, you completed? And Sydney, Stephen said he's willing to do another engine. So you guys will go today. And then I added in, so Leo and Charlie, you'll go. I'll bet Gavin, Anthony and Micah, and Nate and David. So you guys are going to have time. It doesn't take extremely long to boroscope. So even though I have 1, 2, 3, 4, 5 groups and just 3 engines, like you should be able to rotate through. So share boroscopes. Anna will be out there helping you with that, as well as Nick. And then so. Zach, does that schedule match this one? I think it does.
Yeah.
Cause I revised it a couple times.
Yeah.
Thank you, Austin.
Yeah, you're good.
Okay, so I do have the schedule back there if you're confused about what's what.
The
Any,
four scope, which lab is that?
lab 11,
11.
and that's for scoping the compressor section. So lab 11, lab 6, the rest of you will do Moodle except for Dan and Zach, and Lee, and
He'll probably be back by then.
he should. Let me think about this
It's
for
only
a
like
second.
an hour passing, it should be fast.
Because there's stuff, I need everybody to be together. So, well, let's see, Sam, John, they're scoping. I could do, let's see, Austin and John. You just have Moodle labs, or is there anything else you're in the middle of? Would you like to be swapped out and do a King Air run today?
Yes.
Okay, so I'm going to swap that since Isaac, I'll bump you to whatever slot they had.
I'm gonna draw on.
Sorry.
I'm gonna draw on this one that's split.
Yeah. Yeah. But Lee, if you want to double up, you can totally sit in on their run, and then you will have your own run. But you're welcome to join us. So, we're doing, okay.
5 minutes, dude.
21,
Okay,
so, Dan and Zach, Austin and John, I will meet you in 5 minutes. I need a little break. Here at this PT6, I'm going to go over some stuff of what's happening when we're starting, and then we'll go together out to the King Air. The rest of you, Anna and Nick, are in the lab, so if you have questions, ask them and stuff.
Is there a lab for the King Air?
No, so it's not an ACS item. It's just a cool thing that we're fitting in because I can't teach turbine without running a turbine.
my time is